Okay, so today I'm going to talk a little bit about an instrument that we've been developing over the last couple of years called ExCALiBR. So we're a little bit farther back down the TRL scale. We're currently at Trl-4, and this is an instrument that we're developing to be able to analyze organics in lunar regolith. And we have many team members. They didn't all fit on the title slide, so I put them all here. This is an instrument we've been primarily developing at NASA Ames Research Center. And we've had support from Shell, and on the analysis side, support from NASA Goddard and Impossible Sensing, which is a company in St. Louis, who's developing a custom Raman spectrometer that fits with Excalibur, which I'll talk about a little bit later. So to start, I just want to talk a little bit about why we think organics on the moon are really exciting and why we want to analyze them. So we know from LCROSS that there were organics detected in PSRs, and then there was some reinterpretation of some of the Apollo samples done by Jamie Elslow's group at Goddard, looking at amino acids in some of the Apollo samples. So we know that there are organics, and particularly in volatile-rich regions, we think there could be potentially a pristine repository of some of the organics that were also delivered to early Earth. And so this could be, this is really exciting because as we know, that record on Earth has been wiped out for the most part of that very early part of, prebiotic chemical evolution. There's also the potential for there to be raw materials for ISRU to be detected, and some cases potentially that are rare of reworked Hadean terrestrial samples that have been preserved on the moon. So there's some cool science to be done there. And then from the astrobiology perspective, looking at the organics in these PSRs could be really interesting abiotic controls for future life detection missions. This is an opportunity for us to understand or improve our understanding of what organics look like in a non-biological planetary environment where there's lower risk of terrestrial contamination, kind of avoiding some of those problems we have with looking at abiotic organics on Earth. So the instrument, our instrument science goal is to try to understand the sources of lunar organics that are detected. So that could be exogenously delivered, like meteorites, organics that are synthesized in situ, or material that's been sourced from Earth. And so what we want to do is be able to characterize the structural makeup of those lunar organics. So look at the classes, the functional groups, and the distributions of these molecules at the selected landing sites to sort of constrain how they were made. So our primary molecular targets are lipids and hydrocarbons. So lipids are the most abundant preserved soluble organic on Earth. They are required for life. They make up membranes, and they also have the longest lifetimes in the rock record. So they're very robust molecules relative to other types of organics. Abiotically, they're also very abundant. And so on the bottom right, you can see a pie chart of all of the soluble organics in Murchison. And 60% of these are hydrocarbons and lipid-like hydrocarbons. So this is really what we're going after, is this most abundant fraction of what might be there. So Excalibur is using a different style of approach to looking at organics than what's been classically flown. We're using liquid extraction or solvent extraction. And what we want to be able to do is, the reason we're using this is because we want to be able to look at the structure of organics. And when you extract the organics out of the rock in the liquid phase, you maintain those diagnostic structures. So you can look at the products that are delivered to your analytical instrument, and you're able to connect those structures back with the original structures. And that kind of helps us deduce origin. And these have a very high, what I call terrestrial heritage. They've been used on over 70,000 terrestrial samples. So there's a lot of work in developing and optimizing these techniques that we've been trying to automate and integrate into our instrument. So Excalibur has a number of sample processing steps to accomplish this goal. And by doing the steps in this way, we can get at lower limits of detection than what's previously been possible. So the first step is we accept about 25 cc's of regolith, which is quite a bit. It's a larger volume than other types of instruments, but that also helps us increase the signal that we supply to our analytical instrument. Then the sample is ground up. We're using a modified rock blender design. And then within this chamber, we add organic solvent and we sonicate it, and that helps move the organics into the solvent that we've added. Then that material is passed through a filter. The inorganic material is filtered out, and our solvent containing our organics of interest is then put into a bottom chamber, where we then evaporate off by just pulling a vacuum the solvent, and we're left with a residue of just the organics on a transparent window. So by concentrating the sample like this, we also help to increase our signal. So then from there, we're compatible with a number of different types of analytical techniques. We've looked at GCMS, for example, and laser desorption, mass spectrometry. But the one that we're thinking about targeting for the moon right now is trying to couple to a Raman Ceres, which I'll talk about in my next slide. So the idea is that this transparent window is coated with gold nanoparticles and allows us to do surface enhanced Raman spectroscopy. And here on the right is our Trl-4 breadboard that's right now operating in the lab. We're in our final month of validation before we move on to the next phase of our project and starting to work towards getting to Trl-5. So it's been, our project was funded in 2019 by STMD. So a lot of this development happened throughout COVID in people's garages. So I'm pretty happy with our progress, and we've made a lot of good advances this year now that we've been back in lab. And so once Excalibur has performed its extraction steps, we've worked with this company called Impossible Sensing that I mentioned earlier to develop a custom Raman spectrometer that interfaces with Excalibur. And with Merlin, thank you. We've been able to demonstrate PPT, parts per trillion detection limits when coupled with Excalibur using some polycyclic aromatic hydrocarbon standards. And so the top of Merlin is where the bottom of Excalibur will sit, and we can look at our extract, our residue extract, through this transparent window with their green laser Raman. And I just wanted to show a little bit of the results. This is one of the most complicated samples that we sent them to work with and try to optimize. We were successful in analyzing a complex natural sample. All of the major lipid bands that we expected to be present were present. There was diagnostic information about the types of organics present, and was consistent with some of the GCMS data from this particular sample. So far, we've been really pleased with our progress and the results, and our ability to look at organic structure and content with this technique. So finally, where we're at now, so we have 2 Trl-4 prototypes. We just finished a proposal to DALI last month for funds for maturation, and we hope to build a combined instrument that would be relevant to future CLIPS landers, where we would take sample, apply all of our processing steps of grinding, extracting, filtering, concentrating, and then finally analyzing it with Raman. And that's it.